So hi guys, in continuation of our lecture from the last time where we looked at the first case study in converting an inexact differential equation to an exact differential equation, we are going to be taking a look at the second case study in obtaining the integrating factor which will be used to multiply an inexact differential equation in order to convert it to an exact differential equation. So here we are considering f to be a function in y only. So let's represent f as a function in y. So this means f subscript x, which is the same thing as the partial derivative of f with respect to x, must be equal to 0. And f subscript y, which is usually the partial derivative of f with respect to y, is now equal to the total derivative of f with respect to y. And this is because f is a function in y only. So from equation asterisk that we obtained in the previous video, I will write it. We have f subscript y multiplied by p plus f multiplied by p subscript y should be equal to f subscript x multiplied by q plus f multiplied by q subscript x. So this is our equation asterisk. By substituting the necessary values, we now have that p df dy plus f multiplied by p subscript y must be equal to, recall that f subscript x is equal to 0. So we have the first term of this equation on the right hand side to be equal to 0. So this will be equal to f multiplied by q subscript x. So just as we evaluated in the previous video, we'll divide both sides by fq. So we have p divided by fq df dy plus f divided by fq. Oh, sorry, we'll divide both sides by fp instead. So it's going to be fp, not fq. fp, p divided by fp df dy plus f divided by fp multiplied by p subscript y to be equal to f multiplied by q subscript x divided by fp. So by simplifying this and cancelling out the necessary fractions, we have that 1 over f df dy plus py or p subscript y divided by p must be equal to q subscript x divided by p. So on collecting the like terms, we have 1 over f df dy should be equal to qx divided by p minus p subscript y divided by p. So we have that 1 over f df dy will be equal to 1 over p, two brackets, qx minus p subscript y. So we can write this in the expanded form as 1 over f df dy be equal to 1 over p multiplied by the partial derivative of q with respect to x, which is q subscript x, minus the partial derivative of p with respect to y, which is p subscript y. So we can now rewrite this as 1 over f df dy. Because this is, we represented f as the small letter before, that's why I'm writing this as f. So we said f is the same thing as f of y. So I'm doing this in order to avoid confusion, since we represented in the first case study f as a capital letter F, that is f to be equal to a function in x this way. So now to rectify that, I'm using this small letter so we won't get it confused. And likewise on the right hand side, you use small letter r just to distinguish them. So we have this where r is represented as 1 over p the q dx minus the p dy. Now, just like we did in the first case study, our original equation is given as p dx plus q dy is equal to 0. So on evaluating this, if r, which is equal to 1 over p multiplied by the partial derivative of q with respect to x minus the partial derivative of p with respect to y, gives a function in y only, that is r is a function in y only, then that means 1 over f the f dy is equal to r, which is a function in y only. So on doing this, you can use separation of variables yet again. So by separation of variables, we have that df divided by f is equal to ry dy. So df divided by f is equal to ry dy. You can then integrate both sides to obtain our value for f. So integrating both sides, we have the integral of df all over f to be equal to the integral of r, which is a function in y only with respect to y. So in evaluating the left hand side, we have ln f, which is a function in y only as we assumed from beginning, to be equal to the integral of ry dy. So using our laws of logarithm, we have our function fy, which is our integrating factor in this space, to be equal to e raised to the power the integral of ry dy. So this gives our integrating factor when f is a function in y only, and our r, which is equal to 1 over p the partial derivative of q with respect to x minus the partial derivative of p with respect to y, is a function in y only. So these are the two case studies that we consider when trying to get an integrating factor to convert an inexact differential equation into an exact differential equation. So to summarize the results obtained from the two case studies, here's what we need to know. So this is just like a summary of everything we've been talking about as regards obtaining the integrating factor. So we have that for an inexact differential equation, p dx p dx plus q dy is equal to 0. From the first case study, we have that if the p dy minus the q dx, that is the partial derivative of q with respect to x, divided by q is a function in x only, or is a function of x only. So let's call that Rx, just like we did in the previous video. Then it means our integrating factor, called as IF, is equal to e raised to the power of the integral of R of x dx. So this is the summary of the result obtained from the first case study. For the second case study, if the partial derivative of q with respect to x minus the partial derivative of p with respect to y divided by p is a function of y alone, we could call that ry. Then we can say the integrating factor is equal to e raised to the power of the integral of ry dy, or with respect to y. So this is the summary of the result obtained in the second case study. Now, to be specific, or to make a bit of an emphasis on this, if after trying the first case, if you try to evaluate the p dy minus the q dx divided by q, and you don't get a function of x only, you can go ahead to try the q dx minus the p dy divided by p to get a function of y only. Then we can, from there, we can get our integrating factor as e raised to the power of the integral of the results that we've gotten from by evaluating the q dx minus the p dy divided by p with respect to y. So these are the two most common cases when we are solving, when we want to convert an inexact differential equation to an exact differential equation. So just to give a brief rundown, the first thing is to test if the equation is an inexact differential equation. After testing that, we then evaluate either of the two cases. Start from the first case, the case study 1. If it doesn't work, then we go ahead to evaluate case study 2, which will most likely work. Then, on getting our results, we evaluate the integrating factor, which we then use to multiply the original equation p dx plus q dy is equal to 0 to obtain an exact differential equation. So in the next videos, we are going to be solving some examples on this concept. Thank you very much for watching this video.